Okay, great. Welcome back, everyone, from the lunch break. So far you've been diving deep into quantum algorithms, where you're essentially using quantum computer to solve a problem. Um, Usually to get some kind of practical advantage for using like Grover's algorithm, you would need your qubits in the order of hundreds of thousands, if not million. And then the question becomes, what can we really do with the nearest term devices, right? Where we have qubits in the order of few hundreds or less than 100, and the qubits are very noisy, right? So I said specified the size, but the quality of the qubits is also very important. And this is where the idea of variational quantum algorithms come in. And so this is going to be a lecture on variational quantum algorithms, two popular ones being the eigensolvers and the QAOA, which Sebastian went through in his lecture yesterday. Um, so before we get started, I need to, yeah, don't worry. My lecture is not related to growers at all, so you won't have to worry about it. But please do feel free to watch it later, as we'll have the recordings available. Okay. So, okay, so let's first of all, let's do like a refresher of terminologies, because I'm going to use them, and I do not want to cause any confusion. So first of all, I want to start with the classical definition of expectation value. And by that, what I mean is consider you have a random variable. I'll use a different color. Okay. So consider you have a random variable x that takes the values. So this is the capital X that takes the values x1, x2, x3, x4, and so on and so forth. Each of them with probability P1, P2, P3, P4, so on and so forth. So I said that P forms a valid probability distribution. So let's say I equals to 1 to n, Pi is 1 because probabilities must sum to 1. So can someone tell me what is the expectation value of this random observable X? Sorry, not observable, random variable X. So I'm not getting into anything quantum, but given the definition that I just provided, 1 over n. So I would like to have a formula that will tell me how the expectation value of x is related to these numbers x1, x2, x3, x4 with probabilities p1, p2, p3, p4, right? So this is sort of a definition that I'm looking for. Sigma xi pi, absolutely. Thank you, Christopher. So yeah, that's correct. So the definition of the expectation value is you take your take the value that the random variable x will take, multiply that with the probability. Sorry, I said x. So sum over, let's say j, xj, pj, okay, from 1 to n. So it will look something like this. Okay, so it will look like p1 x1, p2 x2, so on and so forth, right? Pn xn. So this is the definition of expectation value of a random variable in the way we know the classical probability theory, right? Now, what I would like to get into is using this same idea of expectation value of a random variable. I would like to talk about expectation value of something called this observable, usually represented by H. Okay, so now we're getting into quantum computing. This observable is an operator. So for example, let's say this observable is something like Z1, Z2. So let's say I have 2 qubits. This basically means I have identity, sorry. Let me start my index with 0. So let's say Z0, Z1. So it would look something like, let's say I have 2 qubits, then it would look something like this, right? So now we're getting into the quantum computing. So actually, let me make it even simpler. Let me just use a single qubit where the observable is just Z. Okay, so I only have a single qubit, and this operator is just the Z acting on the 0th qubit or the first qubit. Okay, so the definition of the expectation value of this operator is still the same thing. Okay, the definition doesn't change. Now I'll tell you what changes. Okay, so still the same thing, but what values does Z give? So the definition of this is just this guy. Okay, so we saw, this is also represented by this matrix, right? So what are the value if I measure on a computational basis, right? So if you have a circuit, some gate, let's say like U gate, right? You start with state 0, and then I measure on computational basis. What values do I get? What are the possible values I can get when I measure this? Remember, in the classical context, this random variable was able to take these values, right? X1, X2, X3, X4. In the same manner, in quantum computing, this observable also takes discrete values when it is measured. So let's say I measure some state at the end. What value do I get? What are the possible values I can get? There are only two outcomes. Okay, that's the hint. What are they? Anyone willing to make a guess? 0 or 1. Excellent. So if you measure your qubit, it's going to be in either state 0 or in the state 1, right? Very good. So we measure those, we get those states as outcomes, but when we're actually talking about the value that we measure, it's actually the eigenvalue. So if you measure state 0, then you get the eigenvalue +1. Why? Because Z has eigenvalue +1, right? So the definition of eigenvalues, okay, so maybe I should also get into this. Okay, still a recap. So the definition of eigenvalue is, okay, so this is not quantum, this is classical. So the definition of eigenvalue is if you have a matrix H acting on a vector V, it gives you by some eigenvalue, let's say lambda, let's say act on vector Vi, and then gives you this eigenvalue lambda and the vector Vi, right? So if this is the case, then lambda is the eigenvalue. This is linear algebra, right? Lambda is the eigenvalue corresponding to vector Vi of H, okay? With the same definition, then in the case of the quantum case where you have an operator, so what happens if I apply Z on state 0? What do I get back? What do I get back when I apply this Z operator on 0 state? Anyone? I get back the 0 state, exactly. So I get back the same state, right? And if I apply it on the 1 state, I'll get back the -1 state, right? Now this has +1 in front of it, right? So that means the eigenvalue is +1, and the eigenvalue here is -1, okay? You can also read it off just by looking at this operator, because this is in something called spectral decomposition form, which means you write your operator in terms of its eigenvectors in this manner, okay? And you can see that this is your eigenvector written as Brian Kett. This is the eigenvector written as Brian Kett. So that means the coefficients will just be the eigenvalue. So this has eigenvalue +1, this has eigenvalue -1, okay? So this is just a refresher on what eigenvalues and eigenvectors are, just written in terms of the bracket notation, okay? Now using this definition, if I look at the expectation value of this observable, right, then I will get X. So these are, this guy has two different possibilities, right? So the X's here, because when you measure an observable, what you get is this eigenvalue. Okay, that's very important to remember. let me just write this down. So when we measure any observable, this observable is usually a Hermitian operator. Hermitian operator is, the definition is just this guy. Example would just be this Z operator. X operator is Hermitian, Y is Hermitian, all of these are Hermitian, okay. Without using the jargon, when you measure it, what you get is you get eigenvalues as outputs. Okay, so you're basically measuring the eigenvalue corresponding to its eigenstate. Okay, so that means that if I measure this Z, for example, okay, so now if I measure the operator Z, what I'll get is I'll get the eigenvalue +1, which means I measure my qubit in the 0 state with some probability P1, and then I'll measure the eigenvalue -1 with some probability P2, right? Where P1 plus P2 is just 1. Now just go back to the definition of, classical probability theory, where we define expectation value of a random variable, right? It was just like this. And the same thing follows in the quantum case, except the random values or the values of this random variable are going to be the eigenvalues. Okay, is this clear? Can you give me a thumbs up if it's clear to you? And if not, please ask me a question. Okay, I see 2 thumbs up. Okay, I see multiple thumbs up. Excellent. Okay. Please feel free to ask it, whether you feel comfortable asking by unmuting yourself or whether you feel comfortable asking just on chat, either is fine. Okay, so with this, now let's get into the theory of variational eigensolvers, or I would say variational quantum computing or variational quantum algorithms, whatever you call it. All of these use just the same principle, just different names, but just the same principle. Okay. Now that you know this, let me look at my note if I need to first clarify anything else. Yeah, I think we look good. So I will have to switch between my iPad and slides today as well, but I'll be very mindful of what I'm sharing. And please remind me if I am not. Okay, so the theory of variational algorithms. So let's get to it. All right. So you probably heard of this before. This has been referred to multiple times, but okay. Variational quantum eigensolver is a hybrid quantum classical technique that is used to determine the smallest eigenvalue of a large matrix or Hamiltonian H. Okay, how does this work? Just like in the example of QAOA, or even in the example with the rotation gate that Sebastian used yesterday. How does this work? So the goal of VQE is to essentially look for a set of parameters, thetas. So I'll get into the quantum circuit later, but think about a set of parameters, thetas, that will minimize this expectation value of this Hamiltonian H, right? In my example, my H was just Z on a single qubit. And so the goal of this is basically to prepare such a state, or rather to find this optimal parameter theta that will minimize this, okay? Now, obviously, this needs to obey some kind of principle. What I mean by that is this needs to have a upper bound, right? Or needs to have a global minimum. If not, then, if it doesn't have a global minimum, then there's a problem. But thanks to quantum mechanics, or the variational principle of quantum mechanics, that tells us that this thing actually has an upper bound to the smallest eigenvalue of this Hermitian observable or Hamiltonian H. Okay. So what is expectation value? I just went through this. And the question is, can you prove this? see something in chat. Can you describe what the problem is if there is no true global minimum? Yes, so if there are multiple, let's say global minimas, then either solution will be fine. So essentially, if there are multiple solutions, then your theta corresponding to either solution should be fine. However, the problem is, I'll get into this later, and this is the problem of barren plateaus where you have multiple local minimums and you get stuck in a local solution, a local minimum that gives you a suboptimal solution, right? Not the optimal solution, which is the global minimum. Okay. So I don't want to give this to you just as a, as a bullet point, but I actually want us together to prove this in some sort of way. But it will be guided by me. So any thoughts or any intuition on why this makes sense? Why does this need to have this upper bound on the smallest eigenvalue of H? Because remember that this psi theta can be any trial state, any state, arbitrary state, right? It's not its eigenstate. So that's something we need to get into. I would not expect you to be able to prove this unless someone has a background in quantum mechanics. Okay, so let's get to this. So I use this terminology, spectral decomposition, that basically expresses your observable in terms of its eigenvalues and eigenvectors. Simply written in bracket notation, it looks like this. Okay, just like Z was written as, for example, ket0 bra0 with eigenvalue +1 and ket1 bra1 with eigenvalue -1, right? But you can do this for any H like this because H is Hermitian. And there is a theory that proves that you can have this decomposition for any Hermitian H. Okay. So what we can do is psi of theta here. We can actually write this as a linear combination of eigenvectors of H. Okay. The reason for this is this psi i's, this actually forms a basis for your Hilbert space. And you can write it as sum of coefficients of so basically your goal is to find this optimal coefficient, but you can express it like this. And if you substitute this back into the equation that I showed earlier, which is this guy, this E of theta, then you'll get this expression. Okay, and you can trust me, you can get this. I really like it if you took a time later on to sort of like get to this stage, because you'll familiarize yourself more with the Dirac notation. But if not, that's also fine, because you can take this for, some algebraic steps and you got here. Okay, so that's fine as well. Now I want you to look at this, pay attention to this expression, and you can trust me that this is correct. So this tells us that E of theta can be expressed in this manner. Okay, and we said that this has an upper bound on lambda 0. Can you see this Y? Now see that these numbers are all positive numbers, correct? Because this is norm squared of alpha I, which is a complex number. Can you see why this has an upper bound on lambda 0? Can anyone post on chat why that would be the case? Let's give a few seconds to look at this expression first and see why. So this is going to be, for example, substitute, sorry, I said lambda 0, lambda 1 in this case, because I'm starting my index from I goes to 1. Any intuitions? Okay, so maybe it's not that straightforward, but it is also not non-trivial. So let me just share my iPad and actually show this to you. And then with that, then we'll get into other things. Okay, so this is quite a strong principle, and you'll see why. So E of theta, which was defined as expectation value of this trial state that we prepared, the observable that we're trying to measure in this manner. is this guy, and then I told you that this is I equals to 1 to n alpha I of theta squared of times lambda I. Okay, and lambda I are the eigenvalues. Okay, good. Now the question is really, remember that I wrote my psi of theta, the trial state, as linear combinations of these coefficients. These are complex numbers times psi I. Now, assuming that this state is normalized, what is the criteria on the coefficients for this to be normal, for this state to be normalized? Anyone? Remember that the coefficient squared is just the probability, right? So this again, like viewed differently, is just the sum over I, pi lambda I, where this is the probability of getting the state and this is just the eigenvalue. And the probability of getting a state is just the norm square of the coefficient, right? You guys learned this. This is quantum mechanics. So what is, if this state is normal, then what is the criteria on this guy? You can probably also see it from here. What should these coefficients satisfy? There is one equation. The hint is it has to be a valid probability distribution. Can anyone make a guess?
1, I think, not more than 1.
Yeah, exactly, right? So it needs to sum to 1. Excellent. So that means that sum of all of these coefficients needs to go to 1. Okay. So what I would like to do is, okay, before I even get into this, to prove. So I want to prove that E of theta is actually bigger than or equal to lambda 1. That it always has to be bigger than lambda 1, regardless of whatever trial state I prepare. Okay. To prove this, what do I want to do? I want to look at the I know. So this is what I know, or this is what is given to me. I would like to isolate this term, right? So I would like to write this as, okay, I won't use the theta in the parentheses anymore for simplicity. So I'll just say alpha 1 square, lambda 1, alpha 2 square, lambda 2, 3 square, lambda 3, so on and so forth, alpha n square, lambda n. Okay. So to prove this, what can I do in this step? Remember, I want to isolate lambda 1, but it has this coefficient, right? Now remember that the probability can be between 0 and 1. So if I would be able to claim this very easily. I would be easily able to claim that this just has to be bigger than this. Why? Because this is a positive number. Actually, no, I can't do that. I cannot do that because the eigenvalues can be negative. Remember that. So yeah, there is one thing I need to use. And the hint is this guy. Okay. So how can I isolate this lambda 1 term? Okay, let's write this a little bit simpler. So this is just alpha 1 square plus alpha 2 square, alpha n square equals to 1. Okay. What can I do here in this step to isolate lambda 1? Pay attention to this. So hint is here. Anyone? I think I heard Basha say something. Are you muted? Because I think people can't hear you, or is it just me?
Yeah, 1 minus, I think.
Yeah, great. Oh, sorry, I haven't been reading the chat. Okay, great. Yeah, absolutely. So, sorry, Sharif replied this a while ago. So I need to also look at my computer and not just my iPad. Yeah, that's correct. So thank you, Sharif. All right. So what I'll do is I'll just need to do 1 minus, just do 1 minus the other coefficients, right? Alpha 2 square, alpha n square times lambda 1. So this is my first term. And then the rest of the terms just come here. Okay. Lambda 2, alpha 3 square, lambda 3, alpha n square, lambda n. Okay. Now my lambda 1 is alone because 1 times lambda 1 is just lambda 1. Right? Remember, I have a minus times the whole thing. And what I have is, I just take the multiplication of alpha 2 square with lambda 1 minus alpha 3 square with lambda 1 minus alpha n square with lambda 1, right? But I still have this, don't forget. Okay, so this is the other term. Okay, very good. So now this is just what? Lambda 1. Now I can combine the terms, right? How can I combine the terms? Do you see the similarity here, here, and here? Subtract that. Okay, that's previous text. How can I combine these terms? Anyone? How can I basically simplify this step into this? Factor out the alphas. Excellent. Okay, so I would like to factor out the alphas because here I have alpha 2 square as common, alpha 3 square as common, so on and so forth. So what I'll do is I'll write it as a plus, and then it will be lambda 2 minus lambda 1, right? Similarly, I'll have alpha 3 square, lambda 3 minus lambda 1, so on and so forth, alpha n square, lambda n minus, right here, plus alpha n square, lambda n minus lambda 1. Okay, very good. So I didn't state this earlier, but what I could do is I could assume that the way I index these lambdas, I can just assume that lambda 1 is less than lambda 2, is less than lambda 3, is less than lambda n, right? I can assume this basically because it's going to have n different eigenvalues. And I can assume that I'm calling the smallest one lambda 1, the second smallest lambda 2, so on and so forth. Okay? So what can I say now? Can I say this? So using this, what can I say now? Because this is a positive number already. What can I say about these terms? Are they positive or negative? Please unmute yourself, or are they all positive terms? Yeah, so they're all positive because you know, because I arrange them in that way, right? So because lambda 2 is bigger than lambda 1, right, which is here. Lambda 3 is also bigger than lambda 1, so on and so forth. Okay, great. So that means I can just say that this is bigger than or equals to lambda 1. Why? Because this is a positive number. Remember, probability is a positive number, and this is norm squared, so you can see that as well. This is a positive number, so on and so forth. Okay, so this is the variational principle of quantum computing or quantum mechanics, let's say. And this is all where so what is the implication of this, right? This actually has very nice implications for us because I said that what I want to measure some observable or Hamiltonian, right? But I can use any trial state I want to, right? As long as this is a normalized state, normalized value state, I can use any trial state. So that means now let's go to quantum computing, right? So this is more like quantum mechanics right now. So in the context of quantum computing, the implication is that I can start my qubits in state 0, like this, right? But that's by default is the case. But I can apply any unitary gate u of theta. And when I measure this observable, h, or let's say, for simplicity, let's say I measure in computational basis, then I know that this is always going to be larger than its smallest eigenvalue, okay, which is the -1, right? Because it has +1 and -1 as eigenvalues. So here I'm assuming that I'm measuring all qubits, by the way. If I'm measuring a single qubit, that's also fine. Okay, so like this, let's say. All of them are done in Z basis. So the implication of this is that whatever the output in this quantum circuit is, so basically it's going to, when you measure it, you're going to measure 0, 1, 0, 1, 0, 1, 0, right? Let's say you measured, for example, 0, 1, 0, 1, 0, right? So this is state 0, 1, 0, 1, 0. What is the eigenvalue corresponding to this state? Can someone tell me? Of this observable, let's say Z, 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 Z. What is the eigenvalue corresponding to this observable? Okay, first of all, what are the possible values? Possible eigenvalues. I told you that this single Z has two eigenvalues, right? +1 and -1. What about when I have multiple Z's together? What are the possible eigenvalues? Anyone? Make a guess, maybe? Any guesses? Okay, so the answer is still 2, okay? So the possible eigenvalues are still +1 and -1. And let me tell you why. So this also has two eigenvalues. Why? Well, you can just think of this as, you can separate out. So you can separate out like this, Z acting on 0, tensor Z acting on 1, Z acting on 0, Z acting on 1, Z acting on 0, right? So I don't really need to worry much about what is the state, but I know that whatever the state is, let's say this is Zi, I know that the possible eigenvalues are +1 or -1, right? So 1 multiplied, so I'll have +1, -1 here, +1, -1 here. One of those two. In this case, it's just +1, right? In this case, -1, for example, +1, -1, +1, for example. So I know for sure that this thing is always going to be either +1 or -1 because I'm just multiplying them. Okay, so I can say with a guarantee that if I'm measuring this, the eigenvalue will always be larger than -1. Okay, is that clear? Any questions? So if I actually measure this out, right? Z measure returns you 0. Z acting on 1 will return you -1, right? So I can just count. So how many -1s are there? There are two -1s. So just -1 to the power of 2, and then the same state. Right? So this is an eigenstate because this state, when this acts on this state, it returns me this state with this eigenvalue. Can people give me thumbs up if this is clear? Okay, I see 2 thumbs ups by 3. Okay. What about the rest of the people? 4. Okay, I'm getting more thumbs ups now. 5. Okay, so I'm going to assume that you know this. You get this. If not, please ask any questions that you might have. Sorry, I didn't see this. I don't understand why it's bigger than -1 rather than bigger than or equal to 0. That's a good question. The reason for this is actually, remember that you're thinking of the outcomes of the measurements. The outcomes of the measurements are 0, 1, 0, 1. These are bit strings, right? But these correspond to a state. The expectation value gives you an eigenvalue, not the state, right? So for example, let's do this, right? Let's say you do 0, Z, 0. What are you doing? You're doing 0. So the definition of Z is this guy. So ignore this guy, compute this. Z acting on 0 is just 0, right? So I get +1. Now take expectation value with 1. Z acting on 0 is, Z acting on 1 is what? Z acting on ket 1 is what? It's the state -1, right? So Z acting on 1 is -1. Yeah, exactly. So this is just the state -1. So this has a negative sign, remember? So I just take it out. So this is -1. So that's why it's upper bounded in -1. Is that clear? And the same idea applies to, G, because this also has 2 possible eigenvalues. Okay, excellent. So, okay, so all of this is just to prepare you to actually play around with variational quantum eigensolvers. Okay, so I hope that that you'll remember this. The reason why I wanted to prove it mathematically is because it's such a simple principle, but has like such large implications. Okay. And you'll see where the classical part is, where the quantum part is, so on and so forth.